We will now discuss unbounded operators. And adjoints. So we will now look at linear maps which are not necessarily defined on the entire vector space and also which may not be bounded or continuous in the sense that we have known up to now. The continuous linear operators or bounded linear operators which we have studied so far will come as a subclass of this as a particular case. So let us have V and W Banach spaces. So an unbounded operator linear operator A is a linear map defined on a subspace dA contained in V taking values in W. Okay, so such a map, so it's a linear map, but it can be defined only on a subspace, not necessarily the entire space. So we say D of A is the domain of A. We denote by R of A is the range or image of A. So we say that A is from dA contained in V into W. Okay, so R of A, so this will be contained in V and this will be contained in W. The operator is bounded, is said to be bounded if there exists a C positive such that norm AX in W is less than or equal to C times norm X in V. That's the usual condition. Only now we have for every X in dA, because that is where the operator is defined. Okay, so the it is said to be densely defined. A is densely defined if D of A is dense in V, that is dA closure is equal to V. Okay, then we define the graph of A is set of all X AX, now where X belongs to D of A, and this of course is contained in V cross W. Okay, and the operator A is closed if GA is closed. So the graph of A should be, so this is called the graph of A. Okay, so it's a closed subspace of G cross W, then you say the operator is closed. Okay, so to define an operator we need to specify two things. So to define A we need one D of A, so we have to say where it is defined, and two what its action is, A of X for every X in D. So we have to specify both these things in order to completely define an operator A. Okay, so then the null space of A or n of A equals set of all x in dA such that Ax equal to 0. Unlike non-linear continuous linear operator, you cannot say that NA is closed. However, remark, if A is closed, you can check this very easily, then NA is closed. Now all this terminology is a little bit unfortunate. Normally, logically, we should have first considered these operators and then considered the continuous linear operators or bounded linear operators, which we have been studying hitherto, as a subclass. But historically, this is how it has been evolving, and so we will use this terminology. Henceforth, of course, I will say continuous linear operator to distinguish between bounded linear operators which may not be defined on the whole space. Okay, so for me, a continuous linear operator means dA equals V and A is bounded in the usual as we have been studying up to now. Otherwise, when I say bounded operator, then it may be just defined on dA and not on the whole space. Okay, so let us give an example. Let us take V equals W equals C01, and let us take dA to be C1 of 01, continuously differentiable functions on the closed interval 0, 1. And then you define A of u equals u dash, which is the first derivative of this. So if u is in d of A, then it's a C1 function, so its derivative is continuous, and that's exactly where we are. Okay, so now first of all, A is densely defined, because C1 of 01 is dense in C01. In particular, you have the Weierstrass approximation theorem. Okay, so then its range is entire W, C01, because if you take any continuous function, then its indefinite integral is a differentiable function and its derivative is the given function. So by the fundamental theorem of calculus, you have, so this is nothing but the fundamental theorem of calculus. Okay, then what is n of A? This is just constant functions. So that is precisely the thing. Now, 4. So suppose, what is convergence? So what is the norm here? It's the usual sup norm, which is the norm infinity, and therefore convergence in this norm means uniform convergence. And therefore, if you take un converges to u and aun, which is un dash, converges to B, then we know that is un converges to U uniformly and un dash converges uniformly. Then we know from real analysis course on uniform convergence that U belongs to C1 and U dash equals V. Okay, and therefore this implies that graph of A is closed, that is A is closed. 5. A is not bounded. We have already seen this, that is, you cannot have a constant, so there does not exist C such that norm u dash is less than or equal to C times norm u. And for this we took the sequence, we have already seen this, un of t equals t power n. So then norm u in un infinity is always 1, norm un dash, so norm un is always 1, norm un dash is n, and therefore you can never have a constant like this because C is a finite number. So this is an example. Okay, so now we are going to make an important definition, and for that we need some notation. This is called the duality bracket. So we take x in V and let us take f in V star. So up to now the evaluation I have denoted as f of x. Now I am going to define as f, I should probably write it the other way around, does not matter. So this is fx, and to ensure where we are working, so I will say V star p. So this is a bracket, the first element in the bracket will be the linear functional, and x is the point where it is being evaluated, and this bracket is just the evaluation of these two. And to say where we are working, so we are saying V star and V, and therefore this is a notation for the duality bracket. Okay, so now let VW be Banach and A from dA contained in V taking values in W, a densely defined operator. This is important. Okay. So now we are going to make a definition of a subspace. So Z is equal to set of all V in W star such that there exists a constant C positive, which of course depends on V, such that for all x in D of A we have norm of mod of Vax is less than or equal to C times norm x. So here this is W star W, because V is in W star, Ax is in W, so this is the duality bracket there, and this of course is the norm in V. Okay, so this is Z. So then Z is a subspace that you can easily check. Okay, so if V belongs to Z and x belongs to D of A, define g of x as V evaluated at Ax, again this is W star W. Then mod Gx is less than or equal to C times norm x. So G is a continuous linear functional. So by Hahn-Banach there exists an extension GV to all of V. Why did I leave some space here? I want to write unique extension. Hahn-Banach extensions are not unique, but now it will be unique because dA closure is the whole of V. So if you have something, even in Hahn-Banach theorem we have seen, what is the test of density? If something vanishes, a linear functional vanishes on the space, then it vanishes everywhere. Okay, so that automatically tells you that if you have G which is defined on a dense subspace, then it has a unique extension to all of V. Okay, so G of V is, so GV is again a continuous linear functional. So now GV belongs is in V star. Okay, so starting with something in W star, we have defined something in V star, provided it is in Z. Okay, so we have taken V in Z. Okay, so now we will make a definition. So VW Banach A from dA in V taking values in W densely defined. Z GV Z as defined above, and for V in Z GV as defined above. Okay. Then we set d of A star equal to Z, which is contained in W star, and A star from d of A star contained in W star to V star is defined by A star V equals GB. The map A star is called the adjoint of it. Okay, so this is the so the adjoint is defined for densely defined operators. Of course, A star need not be densely defined, it is defined on Z or dA star, which is some subspace, that is all we know, we have no information other than that. Okay, so the important characterization is if U belongs to D of A and V belongs to D of A star, you have from the definition of GB. What is the definition of GB? Here it is V of AX. Okay, so we have that A star V acting on U. This is V star V, because this is in V star, this is in V. This is nothing but, by the definition, V acting on AU, and this is in W star W. So this is the fundamental defining relationship for the adjoint. And if any map, any continuous linear functional in V star defines this relationship, then it by the density and uniqueness we know that it has to be A star B. Okay, so let us briefly look at continuous linear functionals. So remark, suppose A V to W continuous linear functional. That means dA is all of V and norm of AX is less than or equal to norm A times norm X. Okay, so this we have. Now you take any V in W star, you have that V AX, this is in W star W, modulus is less than or equal to norm V into norm AX, which is norm A times norm X. And therefore you have, so this will be the constant C, and therefore you have that W star is the entire W star is the domain. So the adjoint is defined on the entire space. Okay, so this is information. So if you have continuous linear operators, in fact we will see a little more about this in a theorem at the end of this session. Okay, so let us see some examples. So let us look at finite dimensional spaces. So in a finite dimensional space, all subspaces are closed. Therefore in particular, if you have dA contained in V, finite dimensional, densely defined, dense, so this means dA closure equals V, but dA closure is same as dA because every subspace in finite dimensional space is automatically closed. Therefore when you say in the finite dimensional case, there is it is always defined on the entire space. A densely defined operator is every. So we can, and you know, once you have this, we have already observed that you can define the adjoint on all of the dual space, which is again isomorphic to the same space. So let us take Cn, and then the dual is the same. Okay, so if X belongs to Cn, namely X equals X1 Xn, and if y belongs to Cn star, which is also Cn again, and y equals y1 yn, then you have yx, the duality bracket, is nothing but sigma I equals 1 to n xi yi conjugate. This is the convention. If you have Rn to Rn, then this conjugate won't be there, it will be just sigma xi yi. Now let A from Cn to Cm be a linear transformation. So then A will be represented by some matrix Aij, which is n by m matrix. M by n, sorry, m rows, n columns. Okay. Cn to Cm is m by n matrix. So what is A star yx? So this will be by definition yax. Okay, and therefore that will be sigma I equals 1 to n. Okay, ith component of Ax, that is sigma j equals 1 to n Aij xj multiplied by yi bar. Okay, so now I want to write it in the form ay, a star y acting on x. So I should bring out the x's outside and then bring in the y with, and everything should be in conjugate form for the a star y. So this will be equal to sigma j equals 1 to n of sigma I equals 1 to n a bar ij yi bar xj. And therefore we have, if A star is the matrix A star ij, then it automatically follows that A star ij is nothing but A ji conjugate. Okay, and this is the usual conjugate transpose of the matrix A. So this is how the adjoint works. In case of real, it is just the usual transpose of the matrix. There is no conjugation involved.